So we're going forth from simple harmonic motion now to mechanical waves. We did a demonstration just a minute ago with the slinky where we showed you, first of all, what a wave is, and second of all, the two types of waves. A wave is something that carries energy from one place to the other. Okay, when somebody jumps in the swimming pool, somebody else on the other side of the swimming pool ends up bobbing up and down as a result of the wave that was produced when the person jumped in the swimming pool. Why does the person bob up and down? Well, because of the wave. But what did the wave do? It carried energy from the person who jumped into the pool to the person who was on the other side of the pool. The wave carried energy from one place to the other. It really is just, as we saw in the demonstration we did a minute ago, the simple harmonic motion of individual particles within that wave. You guys saw that red piece of masking tape on the slinky going back and forth. You guys saw that that was oscillatory motion, motion that repeated itself, motion that went back and forth. It was simple harmonic motion. If we put a red piece of masking tape on every other spot on the slinky, we would have found the exact same thing. We would have found that every single particle underwent simple harmonic motion. And that's the connection here. That's why we're doing wave motion right now with simple harmonic motion, is because wave motion really is just simple harmonic motion. It's just a whole bunch of simple harmonic motions taking place at once of all of the individual particles. Now, we got two types of waves here, two types of mechanical waves, that is. The first one is called a transverse wave. The transverse wave is that wave that we saw first in the slinky. That was the wave that looked like the water wave. Motion in which the particles went perpendicular to the motion of the wave. So if the wave goes this way, let's say to the right, then the particles are going up and down, perpendicular to the way the wave moves. Versus a longitudinal wave, where this one's a little bit harder to draw, where we have this series of compressions and rarefactions. In other words, areas where we have a higher density of slinky, lower density of slinky, higher density again, and so on and so on and so on. If this wave is moving to the right, then the particles within this wave are moving right and left, or parallel to the motion of the wave. Both simple harmonic motion. One of them is simple harmonic motion perpendicular to the wave. One of them is simple harmonic motion parallel to the way the wave is moving. Let's write down a couple words for each of these as well, just so that you can remember that when you go back to study it. Let's say motion. This one is motion of the particles. Perpendicular, or 90 degrees. Perpendicular to the motion of the wave. And this one, of course, is going to be motion of the particles that are parallel to the motion of the wave. Let's give you a little bit more detail now with these two types of mechanical waves. The first one being transverse. Okay, let's label a few things on this transverse wave. First of all, you can see that I've got two axes labeled here, the x-axis and the y-axis. The x-axis is going to be the axis upon which this wave moves. It travels along the x-axis. Which way do the particles move if it's a transverse wave? Well, if the wave is traveling along the x-axis, then the particles you can see are going to travel along the y-axis, perpendicular to the motion of that wave. Let's label a couple of different parts of that wave now. Again, when we did our demonstration, we talked about this a little bit. When you have a bump in the wave, something that's below the equilibrium or above the equilibrium or above the x-axis, we're going to call that a crest. It's like the crest of a hill. Okay, when I grew up in Nova Scotia, I don't see these signs on the highway in Alberta. I don't think they use these ones, but when I learned to drive and was growing up in Nova Scotia, you used to go over these hills, and as you were approaching the top of the hill, what you'd often see is a sign on the side of the road that said blind crest. That just meant that you can't see over the hill. Okay, there's a crest to the hill. You can't see over the hill. So be alert. Be aware that somebody could be pulling out of a driveway and you might not see them until the last minute. It was a blind bump of a hill. Okay, the blind top of a hill. The crest of a wave is the same thing. It's the top of a hill. Okay, the bump of a hill. Versus a trough, which is like a feeding trough. Okay, a pig feeds from a trough, a dip. Okay, all the food is in that trough. The pig sticks its head in and it eats what's in it. Okay, this is the trough of a wave, the dip of a wave. So we're going to say the crest is a high point of the wave, and a trough is a low point. The wavelength, this is a new one. The wavelength is literally just the length of a wave. We're going to put in brackets here, though, might clarify it a little bit, the distance over which the wave repeats itself. Now, the symbol for the wavelength is going to be a new letter, a new symbol, one that you've never seen before. The last time you saw a letter from the Greek alphabet was for the coefficient of friction. It was mu. Okay? That has nothing to do with this other than it's a Greek letter, as is the Greek letter lambda. It's like an upside down Y. Spelt like this. Lambda. Lambda is the wavelength of the wave. Why don't they call it W? I don't know, but they don't. Wavelength is always the Greek letter lambda. And you can see that I have it labeled up here. It goes from the top of one crest to the top of another crest, the distance over which the wave repeats itself. Now, we could also label it right here, from trough to trough, or we could also label it right here. Could we label it here? Is that a wavelength? That's a half a wavelength. That's not the distance over which the wave repeats itself. That's half the distance over which the wave repeats itself. So one complete wave distance, or the distance over which the wave repeats itself, all of those ones that we have drawn up there work for us. The amplitude is the height of the wave. But it's the height of the wave as measured from the equilibrium position, as measured from the x-axis. Not from top to bottom, but rather from middle to top, or from middle to bottom. The symbol for amplitude is a capital A. And the amplitude is related not to the wavelength, not to the frequency, which we'll talk about in just a few minutes here, not to the speed, none of that stuff. The amplitude of the wave is related to the energy of the wave. And that should be intuitive to us if we give it a little bit of thought for 5 seconds. A water wave, that exists out in the ocean, they're big water waves, right? Sometimes you have swells in the ocean that are several meters high. Okay, that's not something that you want to be in a little, just a little canoe out there. And why don't you want to be in a canoe out in the middle of the ocean when you've got these giant waves? Because these giant waves carry a whole lot of energy with them. The bigger the wave, the bigger the energy. The amplitude of the wave, the size of the wave, is related to the energy. Where are we going to label the amplitude on here? Well, it's from equilibrium. It's the height of the wave as measured from the equilibrium. So it could be from the equilibrium to the top of a crest, or the equilibrium to the bottom of a trough. I think it was on Boxing Day in 2005, I believe it was. There was a massive tsunami in the Indian Ocean, I believe it was. 2004, was it? Okay. And it killed something like 125,000 people. It was unbelievable, the devastation. And what happened was there was an earthquake in the middle of the ocean, okay, in the middle of this ocean. And this earthquake carries a lot of energy with it, right? There's a lot of kinetic energy associated with this massive earthquake. Well, so what? It's in the middle of the ocean. Well, the problem is you got a whole bunch of water surrounding this earthquake. And what happens? That water carries energy, just like it carried energy when the guy jumped in the swimming pool. Carries energy from one place to the other. Just happens to be a whole lot more energy when there's an earthquake, a massive earthquake like there was there, than there is when a guy jumps in a swimming pool. Carried so much energy, the water carried so much energy from the middle of the ocean to the shore that it literally killed over 100,000 people. It wiped off the face of the earth, entire towns and entire villages. About 30 hours later, believe it or not, about 30 hours later, literally around the world, in Halifax, Nova Scotia, they measured swells in Halifax, outside of Halifax, of about a meter high as a direct result of the tsunami that took place, or as a direct result of the earthquake that took place in the Indian Ocean. Okay, that's a lot of energy. Imagine, okay, if that energy makes it all the way to Canada, all the way to the east coast of Canada, okay, that's an unbelievable amount of energy that it's carrying, okay? And you can imagine why, that wasn't a dangerous swell on the east coast of Canada in the United States, right? But you can imagine if it even makes it there, how much energy must have been there in the first place when this wave was produced. And you're a couple hundred miles from it as opposed to a half a world away. Amplitude, the height of the wave, and it's directly related to the energy of that wave. Here's the other kind of wave. This isn't a very good picture of it, but it's the best I could do with Microsoft Word. This is a longitudinal wave. This is the wave that we showed you second with the slinky, where I kind of pushed my hand back and forth. It created the areas of compressions and rarefactions. The compressions were areas where we had a higher density of the medium, a higher density of the material that carried the wave. The rarefactions were those areas that followed the compressions. That's where it was lower density. And they roughly correspond to crests and troughs. We just don't call them crests and troughs because it's not bumps and dips. It's higher density and lower density. Now, in a longitudinal wave still travels along the x-axis, but this time the particles, they're all still undergoing simple harmonic motion just as they were in a transverse wave, but this time they're going in simple harmonic motion parallel to the way the wave moves, as opposed to perpendicular to the way the wave moves. It's all simple harmonic motion. It's just which way the simple harmonic motion is. Let's talk about how fast these things move. Good news here. We're going to do some mathematics, but it's easy math. Right, Aiden? Speed, of course, is how fast the wave moves, right? That's no different than the speed of anything else. How can we describe the speed of it, though? Well, normally waves will travel at a constant speed unless they enter a new medium. Okay, if it goes from deep water to shallow water, then it will change speed. That's why waves break, by the way, is because when waves come into the shore, they're going from deeper water to shallower water, and as they go from deeper water to shallower water, they change speeds, and therefore they break. They kind of collapse over themselves. But normally, as long as you're not changing the conditions, then the wave will travel at a constant speed. And because of that, because the waves travel at a constant speed, not the particles of the waves, but the waves themselves travel at a constant speed, we can describe their motion by the equation V equals d over t. That's the first equation we learned this year. Well, these questions can't be very hard if we're going to use this equation, right? V equals d over t. But there's another one that we're going to introduce that also describes the speed of waves. V is equal to F times lambda. V stands for speed. Lambda, remember lambda, it stands for wavelength, the distance over which the wave repeats itself, the length of one wave. F stands for? No, not the force, it's a lowercase f. F stands for? We've frequently done this term now over the last month or so. Anybody want to take a guess at what it would be, Elaine? It would be frequency. Good. And frequency, of course, is measured in hertz. Now remember, you might not be given frequency. You may need to find frequency using one of those other equations that you learn for frequency. Maybe you learn it by, or you find it by the number of cycles per unit time. Maybe you find frequency by using 1 over t. None of these should be foreign to you because we've done them in our circular motion unit and also when we did simple harmonic motion. The two main equations, the two basic equations, this one and this one, but you may need to use something else in order to get to one of those two main ones. All in all, though, these questions are really not that hard. You got to pay attention sometimes. Sometimes there's a little trick in them. Okay, maybe you got to divide a distance by 2, or you got to multiply a distance by 2. You'll see a couple examples of that in a little bit. Okay, but if you're paying attention, if you're alert, then really these questions are all pretty straightforward. Let's take a look at an example here. Pretty straightforward one, I think. Page 409, example 8.2. It says, to generate waves in a stretched spring, you oscillate your hand back and forth at a frequency of 2 hertz. In other words, you move your hand back and forth like this 2 times per second. Okay, that doesn't mean that it's going this way 2 times per second. It means that it's going back and forth in 1 second. Two complete cycles in 1 second. The speed of the waves is 5.4 meters per second. What's the wavelength? Well, if our frequency is 2.00 hertz and our speed is 5.40 meters per second, then our wavelength can be found by using the wave equation. Sometimes we call this the universal wave equation. V is equal to F times lambda. Lambda is equal to V over F. V is 5.40 meters per second, and F is 2.00 hertz. What's my wavelength going to be there? 5.4 divided by 2 is 2.70. What are the units? It's a wavelength. So units would be meters, yeah. Now, if you're wondering where that meters came from, here we've got meters per second over hertz, and a hertz is the same thing as saying 1 over seconds. Well, that's the same thing as saying meters per second times seconds over 1, right? We multiply by the reciprocal, seconds cancel, and we're left with meters. So intuitively, you probably could have figured out that the wavelength units were going to be meters, but you could have done it mathematically as well. Is that good? Man, if they're all this easy, then we're set, right? Let's try these 3 questions, please. We'll give you just a few minutes to work on those, and then we'll give you some check and reflect questions, if you're all good with these, that is. All right, guys, let's take a look at number 3 here again. It says, a fisherman anchors his dinghy in a lake 250 meters from shore. The dinghy rises and falls 8 times per minute. He finds that it takes the wave 3 minutes to reach the shore. How far apart are the wave crests? Just the wording of this can kind of throw us off a little bit sometimes. He is 250 meters from shore. In other words, the wave has to travel 250 meters. That's not the wavelength. Okay, the length of one wave is not 250 meters. That's how far the wave will travel if it's traveling from his dinghy to the shore. The dinghy rises and falls 8 times per minute. That's going to be a frequency. But it's not in hertz. It's in cycles per minute as opposed to cycles per second. And we're gonna convert that to cycles per second in just a moment. It takes 3 minutes to reach the shore. Okay, we're going to convert that to seconds as well. We want to find the wavelength here. How far apart are the wave crests? The distance over which the wave repeats itself, that's going to be the wavelength. To find the wavelength, we only have one equation that works there. V is equal to F times lambda. Lambda is equal to V over F. Now V, we don't know what it is, but we do know what F is if we convert that to hertz. Okay, let's do that now. 8 cycles per minute is going to be how many cycles per second? Do we multiply or divide by 60? We're going to divide by 60. If we multiply, we get 480. Okay, if you have 8 cycles in an entire minute, are we going to have 480 cycles in 1 second? No, we're not. So it's got to be divided by 60. What is 8 divided by 60? 0.133. So, sorry. That's not the right place for it. 0.133 0.13 cycles per second, or 0.133 hertz. All right, that's good. We've got that, but we don't know what the speed is. So let's get the speed now. There's only one other equation that we have for waves here, and that's v is equal to delta d over delta t. We know the distance that the wave travels to the shore is 250 meters. The time was 3 minutes, wasn't it? Not 3 seconds. 3 minutes corresponds to 180 seconds. 250 divided by 180 is going to give me 1.3888 meters per second. So if we take that value now, 1.388 meters per second divided by 0.133, I assume we get a number that's 10 meters. Is that good? Make sense? Hold on before you take off here, guys. Yep. I'm sorry? What's your question? All right, okay. So we're good with that, Rucker. Your homework for tonight here, guys, is page 410. Some check and reflect questions. Page 410. Number 1 to 10. Some of these are qualitative questions where it's just a couple word answers. Some of these are math questions like we've done here just now. All right, that's it for today.